Private workloads are called private for a reason, but private does not mean isolated from the world forever. Real workloads still need package updates, container images, license checks, payment gateways, fraud APIs, and partner services on the internet. That is where private outbound internet, or egress, becomes a serious architecture topic. If engineers solve it casually, they create weak routes, uncontrolled exposure, and surprise cost. In production, the question is never just, can this server reach the internet? The real question is how that traffic leaves, what can inspect it, what logs it creates, and what the internet can never do in return. In this lesson, I will show the full egress path. Compare NAT Gateway, NAT instance, Egress-Only Internet Gateway, proxy-based egress, and then step up to the centralized egress VPC pattern large AWS environments use. Let us start with the core idea. Egress means traffic that starts inside your environment and moves out toward another destination. That is different from ingress. In ingress, the user or external system starts the connection toward you. In egress, your workload starts the session first. For the baseline AWS IPv4 path, think of it like this: private EC2 instance or pod, private subnet route table, NAT gateway, internet gateway, and then the external API. That path matters because it preserves the private boundary. The workload can initiate outbound traffic, but the internet does not get a direct route back to start random new connections into that private subnet. Now let us build that design carefully. A private subnet is private because its route table does not send direct internet-bound traffic to an internet gateway. Instead, the default route for internet-bound IPv4 traffic usually points to a NAT gateway. The NAT gateway sits in a public subnet, and that public subnet has a route to the internet gateway. The NAT gateway translates the source address on the way out, keeps track of the session, and lets the response come back to the workload that asked for it. That is why outbound works without publishing the workload itself. For resilience, serious teams usually place one NAT gateway per availability zone and keep private subnets routed to the local NAT in the same zone. That reduces cross-AZ dependency and avoids turning one NAT into a single failure domain. For most teams, NAT Gateway is the managed default for IPv4 private egress. AWS operates it for you, it scales well for common workloads, and it removes the patching and failover burden of managing the network appliance yourself. A NAT instance is the older instance-based version of that pattern. You may still use it when you need custom software, very specific packet handling, or cost experiments at small scale. But now you own patching, hardening, scaling, and failure recovery. An egress-only internet gateway solves a different problem. It is for IPv6 outbound internet access. It allows your private IPv6 resources to initiate outbound traffic while blocking unsolicited inbound connections from the internet. A proxy adds another layer of control. Instead of just forwarding packets, a proxy can authenticate requests, filter domains, enforce application-aware policy, and create cleaner audit trails. In enterprise environments, that can matter more than simple reachability. So what actually uses private egress? Think about private EC2 instances, downloading operating system updates, ECS tasks, pulling images, or EKS pods calling an external API. Now think about a business use case. A payments platform may keep application nodes in private subnets, but still call fraud scoring services, credit bureaus, SaaS identity systems, and software package repositories outside AWS. AI and data workloads do this too. A private service may call a third-party model API, fetch vulnerability feeds, or reach a vendor control plane. The traffic is outbound, but the governance expectations are still high because the data and timing can be sensitive. And not every outbound dependency should use NAT at all. If the destination is an AWS service like S3, DynamoDB, or Systems Manager, VPC endpoints can keep that traffic on private AWS paths and reduce unnecessary internet egress cost. Once you have many application VPCs, many AWS accounts, or stricter compliance requirements, the design changes. Mature platforms do not let every workload choose its own direct path to the internet. Instead, traffic from application VPCs is steered toward a centralized egress or security VPC, often through Transit Gateway. There, teams can place AWS Network Firewall, proxy layers, NAT services, and shared inspection controls in one governed path. That design gives you one place for policy, one place for logging, and one place to review allowed destinations. It also makes security teams happier because internet-bound traffic is inspected consistently instead of disappearing through dozens of isolated NAT paths. AWS prescriptive guidance points teams toward centralized egress for multi-account environments because scale changes the problem. The trade-off is extra routing complexity, more design discipline, and the need to keep segmentation clear so not everything can talk to everything. Here is a production warning people miss all the time. A route is not a security policy. A route table only says where traffic can try to go. Security groups, network ACLs, firewall policy, proxy rules, and destination controls still decide what should be allowed. The next warning is cost. NAT gateways can become expensive when every patch, image pull, metrics export, and service call goes through them by default. Good teams reduce that spend with VPC endpoints, artifact mirrors, caching, and cleaner dependency design. The third warning is availability. One NAT gateway in one zone may look fine in a diagram, but it becomes a brittle shared dependency. Per AZ routing, health-aware failover thinking, and controlled blast radius matter if egress is part of daily application behavior. And finally, log the path. Use VPC flow logs, firewall logs, proxy logs, and targeted reachability testing so you can answer basic operational questions. What left, where it went, why it was allowed, and what failed when a critical dependency stopped responding. So keep the mental model simple. Private outbound internet means the workload starts the session, the private subnet stays private, and the internet never gets a direct invitation back in. Choose NAT Gateway when you want a managed IPv4 default. Choose NAT instance only with clear operational reasons. Choose Egress-Only Internet Gateway for IPv6 outbound patterns. Choose proxy or firewall-centric egress when policy, audit, and destination control matter. If you run many VPCs and accounts, move from isolated egress toward a governed shared path with centralized inspection. That is how top platform teams turn internet access from an ad hoc exception into a deliberate engineering service. At Trustscrin, we are building tools around these governed infrastructure problems, and I will show more of that journey in future videos. For now, if you want the next step, go deeper into route tables, NAT cost reduction, and VPC endpoints, because that is where egress design becomes truly production ready.